This is lab number 3 for Physics 2211 at Georgia Tech. My name is Charlie Romine, and this is my lab report for the black hole problem. So in this lab, we are tasked with building a computational model to show the gravitational forces of a black hole and a star, and then later a black hole, a planet, and a rocket ship, and sort of figure out kind of the interactions that occur between those objects. So some goals of this, first is to demonstrate Newton's second law or the momentum principle. This is applied to pretty much all of our labs and probably will continue to do so because Newton's second law applies to anything that changes direction or speed when it moves, which is just about everything in the world. Also, we're going to discuss universal gravitation, so that big G equals mass 1 times, or the force of gravity equals big G times mass 1 times mass 2 divided by radius squared. And then also rotational motion will play a role in this lab. Some important things like the perpendicular force is equal to mv squared over r. That will play a role eventually. Yeah, so that's kind of some of the ideas. Some more ideas. Again, the F net is the sum of the forces. In this scenario, especially in part 1, there's really only one force, which is a gravitational force. I guess technically in scenario 2, there's the gravitational force of both planets, or not both planets, but the planet and the black hole. And then again, universal gravitation and rotational motion are also both important. So to start, we've got our initial conditions for our black hole in part 1, or for the just scenario. So we've got the gravitational constant, the mass of the star, and then delta T is the number of seconds in a day. So that number comes out to 86,400, I think. But yeah. So then we go through some computation. We find a lot of values through this. The important one is at the bottom on the left side over here is this MBH, which is massive black hole, which we use by rearranging the gravitation equation equals Fg in order to find the mass of the black hole using the other factors that we find earlier. Some important ones to look for are the force, the net force parallel and perpendicular, which are defined above, as well as just sort of our change in momentum in general, as that is equal to F net. On the right side is the arrow code, which is really just kind of like to get the arrows to point in the right direction. So it's not super important, but I figured I would show it. Here are sort of our results. So there's a picture of the model once it is run all one time. The mass of the black hole was found. The formula in the code printed it out over and over again, and I just averaged it to get the best possible result because it's not the same every time because it's not in the middle of the circle. So the calculation is a little bit off. The FNet, the final position, is given there as well as the force in the parallel and the perpendicular direction. Important to note is that the perpendicular direction is significantly larger than the parallel direction, meaning the object was remaining about the same speed most of the time, just depending a little, speeding up and slowing down a little bit based on where it was in reference to the black hole. Discussion in your analysis, discuss parallel and perpendicular. Parallel and perpendicular forces are often compared to the net force. However, they're not always the same. Important differences is that the net force is not only the gravitational force, it's not only the gravitational force, which is often the only one considered in the parallel and perpendicular components. And then the rate of change is different because the net force, while it's changing, the rate at which it changes is not the same as the net force. Part 2, we're then tasked with taking a rocket ship and trying to get it to visit a planet, or to leave from a planet and get close to the black hole. Seeing about as close as we can get. Some important ideas are constant orbit and escape velocity. So the velocity needed to kind of get out of the black hole's grasp so you don't crash into the black hole. Initial conditions, we use the black hole mass that we found in part 1, and the other initial conditions stay the same. And then the computational code on the right is just kind of how we break down a lot of the equations into getting how the rocket moves and how the planet moves. Also important that mine only took like 8 minutes. So the Tmax is 8 times 60, so 8-ish minutes. So this is sort of what my results look like at the end. My initial velocity of the ship was negative 3.87 times 10 to the negative, or to the 7th in the x direction, and 1.5 times 10 to the 6th in the y direction. And then the closest distance it got to the black hole was the number there that you see is the 2.0177 times 10 to the 8th. That is as close as I was able to get it without crashing through some trial and error. Discussion, what if we want to take a look? So if we want the rocket to continue to stay in orbit, then we need to set the velocity. We need to set the perpendicular force of the rotational motion, which is often defined as mv squared over r, equal to the gravitational force, because if those two things equal each other throughout the entirety of the flight, it won't get pulled inward toward the black hole. It will continue to rotate around the outside. So we set the two equations together, we plug in a bunch of numbers, and we get the velocity you see on your screen. That's kind of my best attempt at it. That's how I would set it up. There's probably a little more nuance to this question, but I would set your perpendicular component of force equal to your gravitational force and C